Hello and welcome to Math Zone African Motives. Today, we're diving into a crucial topic in calculus: integration of trigonometric functions. By the end of this tutorial, you will be able to integrate various trigonometric expressions using key identities and substitution techniques. We'll be working through examples from Unit 4.4, covering four main types of problems. First, we'll learn to integrate squares of functions like sine, cosine, and tangent. Second, we'll tackle products of powers of sine and cosine, including those with odd or even powers. Third, we'll cover powers of tangent and cotangent. Finally, we'll look at products of sine and cosine with different coefficients. Our goal is to learn how to manipulate these functions into a form we can easily integrate, usually by changing products into sums or differences. So grab your pens and paper and let's get started. We begin with our first objective: learning to integrate squares of trigonometric functions. Specifically, our focus is on sine squared and cosine squared. To do this, we'll use a pair of essential identities. The first is sine squared x equals 1/2 times the quantity 1 minus cosine 2x. This identity allows us to turn a difficult square into a simple difference of two terms. The second is very similar. Cosine squared x equals 1/2 times the quantity 1 plus cosine 2x. These identities are derived from the double angle formula for cosine. You can see how they convert a squared term into a term that's much easier to integrate. For tangent squared and cotangent squared, the process is even more straightforward. We use the Pythagorean identities. Tangent squared x is equal to secant squared x minus 1, and cotangent squared x is equal to cosecant squared x minus 1. Why are these helpful? Because secant squared x and cosecant squared x are direct derivatives of tangent and cotangent, respectively, which means they are standard integrals. By applying these four identities, we can transform any of these squared functions into a form we know how to integrate. Let's see them in action with an example. Let's apply these identities with our first example. The problem is to determine the integral of sine squared of the quantity ax with respect to x. We can't integrate sine squared directly, so we must use an identity. Our goal is to rewrite sine squared of x using the identity. The identity we need is sine squared theta equals 1/2 times 1 minus cosine 2 theta. Here, our theta is a x. So, substituting a x for theta, we get that sine squared of a x is equal to 1/2 times 1 minus cosine of 2ax. This is the first crucial step. Now we replace sine squared of x in our integral with this new expression. The 1/2 is a constant, so we can pull it out front. This leaves us with 1/2 times the integral of 1 minus cosine 2ax with respect to x. We can now integrate term by term. The integral of 1 is simply x. For the integral of cosine 2ax, we use the standard integral for cosine, remembering the coefficient of x. The integral of cosine k is sine k over k. Here our k is 2a. So the integral of cosine 2ax is sine 2ax, all divided by 2a. Putting it all together, we have 1/2 times the quantity x minus sine 2ax over 2a, plus our constant of integration, c. Distributing the 1/2 gives us our final answer. So, to recap, the process was to identify the correct identity for sine squared, rewrite the integral, and then perform simple term-by-term integration. The final answer is 1/2 x minus sine 2ax over 4a plus c, verified using memo. Our next problem is very similar. Let's find the integral of cosine squared of x. Just like before, we need to use an identity to rewrite this expression. The identity for cosine squared is our key. The identity is cosine squared theta equals 1/2 times 1 plus cosine 2 theta. Replacing theta with a x, we get that cosine squared of x is 1/2 times 1 plus cosine 2ax. Now we substitute this into our integral. We pull the 1/2 constant out, leaving us with 1/2 times the integral of 1 plus cosine 2ax with respect to x. We integrate term by term. The integral of 1 is x, and the integral of cosine 2ax is sine 2ax over 2a. So we have 1/2 times the quantity x plus sine 2ax over 2a plus c. Distributing the 1/2, our final answer is 1/2 x plus sine 2ax over 4a plus c, verified using memo. Next, let's look at the integral of tangent squared. The problem is to determine the integral of tangent squared of x with respect to x. As we discussed, for tangent and cotangent, we use the Pythagorean identities. The relevant identity here is tangent squared theta equals secant squared theta minus 1. Applying this to our problem, we get that tangent squared of x is equal to secant squared of x minus 1. We substitute this into the integral. Now we have the integral of the quantity secant squared of x minus 1 with respect to x. This form is much easier to integrate. The integral of 1 is x, and the integral of secant squared kx is tangent kx over k. Here our k is a. So the integral of secant squared of x is tangent x over a. Combining our terms, the integral is 1 over a times tangent ax minus x plus the constant of integration, c, verified using memo. Our fourth example for squares of trigonometric functions is the integral of cotangent squared. We need to determine the integral of cotangent squared of ax. The method is identical to the one we used for tangent squared, just with the corresponding identity. The identity is cotangent squared theta equals cosecant squared theta minus 1. By substituting theta with ax, we get that cotangent squared ax is equal to cosecant squared ax minus 1. We replace cotangent squared x in the integral with its new form. We are now integrating cosecant squared x minus 1 with respect to x. We integrate term by term. The integral of 1 is x. For the integral of cosecant squared kx, we have a standard result. The integral of cosecant squared kx is negative cotangent kx over k. Our k is delta a. So, the integral of cosecant squared of x is negative 1 over a times cotangent ax. Putting it together, our final answer is negative 1 over a times cotangent ax minus x plus c, verified using memo. For our final example in this section, we have a problem that requires both an identity and a substitution. The problem is to determine the integral of cosine squared of the square root of x, all divided by the square root of x. This doesn't look like our standard forms. Let's start with a u substitution. A good strategy is to set u equal to the inner function, which is the square root of x. Let's define our substitution. We let u equal the square root of x. Next, we find the derivative of u with respect to x. Du/dx is 1 over 2 times the square root of x. Rearranging this, we find that dx is equal to 2 times the square root of x times du. Since we know that u is the square root of x, we can say that dx is 2u times du. Now we substitute all of this back into our original integral. The integral becomes the integral of cosine squared u over u, all multiplied by 2u du. Notice how the u's cancel out, simplifying the expression significantly. This leaves us with 2 times the integral of cosine squared u. This is exactly the type of integral we've been practicing. Now we apply the identity for cosine squared. We replace cosine squared u with 1/2 times 1 plus cosine 2u. The 2 out front and the 1/2 in the identity cancel each other out. Now we integrate term by term. The integral of 1 is u. The integral of cosine 2u is sine a 2u over 2. So we have u plus sine 2u over 2 plus c. The last step is to substitute back the original variable, x, replacing u with the square root of x. Our final answer is the square root of x, plus 1/2 sine of 2 times the square root of x plus c. Verified using memo. We now move on to our second objective, integrating products of powers of sine and cosine. This section covers integrals of the form sine a to the power of mx times cosine to the power of nx, where at least one of the exponents, m or n, is an odd number. The general strategy for these types of integrals is to use a u substitution. Here's the rule. If you have an odd power of sine, you save one factor of sine, Rewrite the remaining even number of sine factors as cosine, using sine squared applied x equals 1 minus cosine squared x, and then use the substitution u equals cosine x. Similarly, if you have an odd power of cosine, you save one factor of cosine. Rewrite the remaining even number of cosine factors as seen using cosine squared x equals 1 minus sine squared x, and then use the substitution u equals sine x. The reason this works is that the saved factor of sine or cosine becomes part of the due term in the substitution. If both m and n are odd, it's often easiest to split the factor with the smaller power. Our first product of powers example is a simple one that can be solved by inspection. We need to determine the integral of sine cubed x times cosine x. This integral is in a special form, f of x to the power n times f prime of x. In our integral, if we let f of x equal sine x, then the derivative f prime of x is cosine x. So we have sine x cubed times the derivative of sine x. The rule for integrating this form is to add 1 to the power and divide by the new power. Therefore, the integral of sine cubed x cosine x is simply sine to the fourth x divided by 4 plus c. We didn't even need a full substitution process for this one. Verified using memo. Now let's tackle a more complex example. This one will require our full strategy for odd powers. The problem is to determine the integral of sine cubed x times cosine squared x. Notice the power of sine is odd. This tells us our strategy. Our strategy is to save one factor of sine, rewrite the remaining factors, and then perform a u substitution. We split sine cubed x into sine squared x times sine x. This gives us sine squared x times sine x times cosine squared x. The term we want to integrate is sin x. Its derivative, negative cosine x, tells us that u should be cosine x. We must therefore rewrite everything else in terms of cosine x. Using the identity, sine squared x becomes 1 minus cosine squared x. This gives us the integral of 1 minus cosine squared x times cosine squared x times sine x. Everything is now in terms of cosine x, except for the sine x that's saved for our do. Let's perform the substitution. We let u equal cosine x. The derivative, do, is negative sine x dx. This means dx is negative do divided by sine x. Substituting u and dx into our integral, we get the integral of 1 minus u squared times sine x divided by negative sine x. The sine x terms cancel. Expanding the terms, we have negative the integral of u squared minus u to the fourth with respect to u. Integrating term by term gives us negative the quantity u cubed over 3 minus u to the fifth over 5 plus c. Finally, we substitute back u equals cosine x. Our final answer is negative cosine cubed x over 3 plus cosine to the fifth x over 5 plus c. Verified using memo. Our third example in this category deals with a product where both powers are odd. We need to determine the integral of sine to the fifth x times cosine cubed x. Since both powers are odd, the rule says we can choose to split either one, but it's slightly shorter to split the one with the smaller power. Here, the smaller power is cosine cubed x. So, we split cosine cubed x into cosine squared x times cosine x. Our integral is now sin to the fifth x times cosine squared x times cosine x. The cosine x factor will be part of our do, which means we must convert the rest to sin x. We use the identity cosine squared x equals 1 minus sine squared x. This gives us sine to the fifth x times the quantity 1 minus sine squared x times cosine x. Now we substitute u equals sine x. The derivative do is cosine x dx. So dx is do divided by cosine x. Plugging this in, we get the integral of u to the fifth times 1 minus u squared times cosine x divided by cosine x. The cosine x factors cancel. This simplifies to the integral of u to the fifth minus u to the seventh with respect to u. Integrating gives us u to the sixth over 6 minus u to the eighth over 8 plus c. Substituting back u equals sine x. Our final answer is sine to the sixth x over 6 minus sine to the eighth x over 8 plus c. Verified using memo. Our fourth example follows the same logic, but we'll be dealing with an odd power of cosine. The problem is to determine the integral of cosine to the fifth x times sine squared x. The odd power is on cosine, so our strategy will be to save one cosine factor and rewrite the rest in terms of sine. We split cosine to the fifth x into cosine to the fourth x times cosine x. Our integral becomes cosine to the fourth x times sine squared x times cosine x. Since cosine to the fourth x is cosine squared x squared, we can write it as 1 minus sine squared x all squared. This gives us the integral of 1 minus sine squared x squared times sine squared x times cosine x. Now we let you equal sine x. The derivative due is cosine x dx. Substituting, we get the integral of 1 minus u squared squared times u squared with respect to u. Expanding 1 minus u squared squared gives us 1 minus 2u squared plus u to the fourth. Multiplying by u squared, we get u squared minus 2u to the fourth plus u to the sixth. This is a straightforward polynomial to integrate. Integrating term by term, we get u cubed over 3 minus 2u to the fifth over 5 plus u to the seventh over 7 plus c. Finally, substituting back u equals sine x. Our answer is sine cubed x over 3 minus 2/5 sine to the fifth x plus 1/7 sine to the seventh x plus c, verified using memo. Let's apply this odd power technique to a problem with a more complex argument. The problem is to determine the integral of sine cubed of 2x times cosine cubed of 2x. Again, both powers are odd. Let's split the smaller one, cosine cubed of 2x. We split it into cosine squared 2x times cosine 2x. This means our u substitution will be u equals sine 2x. We convert the cosine squared 2x to 1 minus sine squared 2x. The integral is now sine cubed 2x times the quantity 1 minus sine squared 2x times cosine 2x. Now for the substitution. We let u equal sine 2x. The derivative due is cosine 2x times the derivative of the inside, which is 2. So due equals 2 cosine 2x dx. Substituting u and dx into the integral, the cosine terms cancel, leaving us with 1/2 times the integral of u cubed times the quantity 1 minus u squared. Distributing, we get 1/2 times the integral of u cubed minus u to the fifth. Integrating term by term gives 1/2 times the quantity u to the fourth over 4 minus u to the sixth over 6 plus c. Distributing the 1/2 and substituting u equals sine 2x back. Our final answer is sine to the fourth of 2x over 8 minus sine to the sixth of 2x over 12 plus c, verified using memo. Here's another example with an odd power, but this time only one trigonometric function is present. The problem is to determine the integral of sine cubed x. The power is odd, so we use the same strategy. We save one factor of sine, rewriting sine cubed x as sine squared x times sine x. The sine ax will become part of our due. Because of the saved sine x, we know we will substitute u equals cosine x. Therefore, we must convert sine squared x into terms of cosine. We use the identity sine squared x equals 1 minus cosine squared x. Highlight L as sin 2x equals 1 towards QS 2x in blue. Our integral is now the integral of the quantity 1 minus cosine squared x times sine x. Now we are ready to substitute. Let u equal cosine x. Then due is negative sin xd. Substituting this in, we get the integral of 1 minus u squared times negative due. The sine x terms cancel. The negative sign can be pulled out front. Integrating term by term gives negative the quantity u minus u cubed over 3 plus c. Substituting back u equals cosine x. We get negative cosine x plus cosine cubed x over 3 plus c. This is also often written with the positive term first. Verified using memo. Our final example in this section is for a very special case, when both powers are even. This requires a different technique. The problem asks for the integral of sine squared of 3x times cosine squared of 3x. There are no odd powers to split, so our previous strategy won't work. The key here is to use a double angle identity. Specifically, we'll use sine 2a equals 2 sine a cosine a. We can rewrite our integral as the integral of the quantity sine 3x cosine 3x all squared. To get this into the double angle formula, we need a factor of 2 inside the parenthesis. We multiply the inside by 2, which means we must also multiply by 1/2 to maintain equality. This 1/2 is also squared to become 1/4 outside the integral. So the integral becomes 1/4 times the integral of sine squared of 6x. Now we have an integral we know how to solve using our first objective. We use the identity sine squared theta equals 1/2 times 1 minus cosine 2 theta. Pulling the 1/2 out and multiplying by 1/4, we get 1/8 times the integral of 1 minus cosine 12 theta is x. This is a simple integral. The integral of 1 is x, and the integral of negative cosine 12x is negative sine 12x over 12. Distributing the 1/8, our final answer is x over 8 minus sine 12 x over 96 plus c, verified using memo. Let's move on to our third objective, integrating powers of tangent and cotangent. Our goal here is to learn how to integrate higher powers of tangent and cotangent, like tan cubed or cot to the fourth. The strategy is to break down the higher powers until we get a tangent squared or cotangent squared. Why? Because we can change tangent squared to secant squared, x minus 1, and cotangent squared to cosecant squared x minus 1. Secant squared is the derivative of tangent and cosecant squared is the derivative of cotangent, making them easy to integrate or use for substitution. Let's start with a simple one we've already seen, just to confirm the formula. We need to determine the integral of tangent squared of x over 3. From our first section, we derive the general formula for this. The formula is 1 over a times tangent ax minus x plus c. In our problem, a is 1/3. Substituting a equals 1/3 into the formula, we get 1 over 1/3 times tangent of x over 3 minus x. This simplifies to 3 tangent of x over 3 minus x plus c, verified using memo. Now let's tackle a higher power, tangent cubed. The problem is to determine the integral of tangent cubed of 3x. We can't use the simple formula we just saw because the power is 3, not 2. We must follow our strategy, split off a tangent squared. We rewrite tangent cubed of 3x as tangent of 3x times tangent squared of 3x. Then we apply the identity tangent squared theta equals secant squared theta minus 1. Distributing the tangent 3x, we get two integrals. The integral of tangent 3x secant squared 3x minus the integral of tangent 3x. We will solve these two parts separately. First, let's solve the integral on the left, which is tangent 3x secant squared 3x. This is in a perfect form for substitution. We let u equal tangent 3x. Its derivative, do, is 3 secant squared 3x dx. Therefore, dx is do over 3 secant squared 3x. Substituting this into our first integral, the secant squared terms cancel, and we are left with 1/3 times the integral of u. The result is 1/6 tangent squared 3x. Now for the second part, the integral of tangent 3x. This is a standard integral. The integral of tangent ax is -1 over a times the natural logarithm of the absolute value of cosine ax. For our problem, it's -1/3 ln of the absolute value of cosine 3x. Combining the results of our two integrals, the final answer is 1/6 tangent squared 3x plus 1/3 len of the absolute value of cosine 3x plus c, verified using memo. Our last example for this section is the integral of cotangent cubed. The problem asks for the integral of cotangent cubed of x over 2. The method for cotangent is a mirror image of the method for tangent. We start by splitting the cotangent cubed term into cotangent x over 2 times cotangent squared x over 2. Then we use the identity cotangent squared theta equals cosecant squared theta minus 1. Distributing the cotangent, we get two integrals. The first is perfect for a u substitution, and the second is a standard integral. Let's work on the first integral. We let u equal cotangent of x over 2. The derivative do is -1/2 cosecant squared of x over 2 dx. This means dx is negative 2 do over cosecant squared x over 2. Substituting this into the first integral, the cosecant squared terms cancel, leaving negative 2 times the integral of u. The result is negative u squared, which is negative cotangent squared x over 2. Now for the second integral. This is a standard integral. The integral of cotangent ax is 1 over a times the natural logarithm of the absolute value of sine ax. For our problem, a is 1/2, so the integral is 2 ln of the absolute value of sine x over 2. Combining our results, the final answer is negative cotangent squared of x over 2 minus 2 times the natural logarithm of the absolute value of sine of x over 2 plus c. Verified using memo. Our fourth objective is to integrate products of sine and cosine with different coefficients. We're considering integrals of the form sine ax sine bx, sine ax cosine bx, and so on. Notice the coefficients a and b are different. To solve these, we use a different set of identities called the product to sum identities. These identities do exactly what they say. They transform a product of trigonometric functions into a sum or difference of functions. Here are the 4 identities you need to know. First, sin A cosine B equals 1/2 sine of A plus B plus sine of A minus B. Second, cosine A sine B equals 1/2 sine of A plus B minus sine of A minus B. Third, cosine A cosine B equals 1/2 cosine of A plus B plus cosine of A minus B. And fourth, sine A sine B equals 1/2 cosine of A minus B minus cosine of A plus B. Notice the order in that last one. By using these, we change a product into something we can integrate easily term by term. Let's apply these identities to solve our first example. The problem is to determine the integral of sine 3x cosine 2x. Here a is 3x and b is 2x. We use the identity sine A cosine B. Substituting our values, we get that sine 3x cosine 2x is 1/2 times the quantity sine of 3x plus 2x plus sine of 3x minus 2x. This simplifies to 1/2 times sine 5x plus sine x. Now we replace the product in our integral with this new sum. We pull the 1/2 constant out front. We now have 1/2 times the integral of sine 5x plus sine x. This is a simple term-by-term integral. The integral of sine 5x is negative cosine 5x over 5. The integral of sine x is negative cosine x. So we have 1/2 times negative cosine 5x over 5 minus cosine x plus c. Distributing the 1/2 gives our final answer. Negative 1/10 cosine 5x minus 1/2 cosine x plus c. Verified using memo. Let's try an example with 2 sine functions. The problem is to determine the integral of sine 5x sine 3x. The identity we need is sine A sin AB. This equals 1/2 times cosine of A minus B minus cosine of A plus B. Here A is 5x and B is 3x. Substituting, we get 1/2 times cosine of 5x minus 3x minus cosine of 5x plus 3x. This simplifies to 1/2 times cosine 2x minus cosine 8x. We replace the product in our integral with this expression. We pull the 1/2 constant out, leaving us to integrate cosine 2x minus cosine 8x. We integrate term by term. The integral of cosine 2x is sine 2x over 2. The integral of cosine 8x is sine 8x over 8. This gives us 1/2 times the quantity sine 2x over 2 minus sine 8x over 8 plus c. Distributing the 1/2 gives our final answer. 1/4 sine 2x minus 1/16 sine 8x plus c. Verified using memo. Our third example in this section is an interesting one that involves a negative angle. The problem asks for the integral of cosine of 1/2 x times sine of 5/2 x. We use the identity cosine A sine B. Substituting, we get 1/2 times sine of A plus B minus sine of A minus B. Notice that A minus B is negative 2x. To deal with the sine of negative 2x, we use a reduction formula. The reduction formula is sine of negative x equals negative sines. Applying this to our problem, sin of negative 2x becomes negative sine 2x. The integral is now 1/2 times sine 3x plus sine 2x. This gives us 1/2 times the integral of sine 3x plus sine 2x. Integrating term by term gives negative cosine 3x over 6 minus cosine 2x over 4 plus c. Verified using memo. There is a smart way to avoid the negative angle and reduction formula altogether. If we write the original integral with the larger angle first, as sine 5/2 x cosine 1/2 x, we can use the identity for sine A cosine B. This leads to a positive angle, sin 2x. The calculation is exactly the same, and we get the same answer. It's a useful trick to remember. We've now worked through 3 different categories of trigonometric integrals. Let's finish with an enrichment problem that combines several techniques. The problem is to determine the integral of sine x times sine 2x times sine 3x. This is a product of 3 terms, not just 2, and the angles are all different. The strategy is to deal with 2 terms at a time. Let's start with sine x times sine 2x. Using the identity sine A sine B equals 1/2 cosine of A minus B minus cosine of A plus B, we get 1/2 times cosine of negative x minus cosine of 3x. Since cosine is an even function, cosine of negative x is just cosine x. So, our integral becomes 1/2 times the integral of cosine x minus cosine 3x, all multiplied by the remaining sine 3x term. Next, we distribute the sine 3x. This gives us 1/2 times the integral of cosine x sine 3x minus cosine 3x sine 3x. This gives us 2 new products to simplify. The first is cosine x sine 3x, and the second is cosine 3x sine 3x. For the first product, cosine x sine 3x, we use the identity cosine A sine B to get 1/2 sine 4x minus 1/2 sine 2x. For the second product, cosine 3x sine 3x, we use the identity 2 sine A cosine A equals sine 2a. This becomes 1/2 sine 6x. Our integral is now much simpler. Plugging these back in, we get 1/2 times the integral of 1/2 sine 4x plus 1/2 sine 2x, all minus 1/2 sine 6x. We can factor out another 1/2, giving 1/4 times the integral of sine 4x plus sine 2x minus sine 6x. Now we integrate each term. The integral of sine kx is negative cosine kx over k. This gives 1/4 times negative cosine 4x over 4, minus cosine 2x over 2, plus cosine 6x over 6, plus c. Distributing the 1/4 gives our final answer. It's a bit long, but we got there by breaking it down into manageable steps. Verified using memo. And that concludes our tutorial on integrating trigonometric functions. We've seen how to handle a variety of trigonometric integrals. We started with the squares, using identities to rewrite them. Then we covered products of powers of sine and cosine, using a substitution strategy based on odd powers. After that, we saw how to integrate higher powers of tangent and cotangent by splitting off a squared term. Finally, we learned to use product-to-sum identities for products with different coefficients, and we combined these techniques to solve a complex enrichment problem. The key takeaway is that for most of these problems, the main challenge is not the integration itself, but the manipulation of the expression using trigonometric identities to get it into an integrable form. Practice is essential to identify which identity to use for each type of problem. Thank you for watching this Math Zone African Motives tutorial. I hope it has been helpful. If you found this video useful, please give it a like and subscribe for more high-quality math tutorials. Goodbye for now.